So welcome back to this YouTube channel. So in the last video, you have looked at the encoder part. Let's say the encoder part of this transformer neural network. In this video, right? So yeah, in the last video we have looked at the encoder part, right? So we have looked at multi-head attention, in specifically, and also how we can get this input and transform this input such that the details of the relation between each of these words in this input sentence will be tracked by this embedding, so just to make sure that the outputs are just to make sure the output output neural network will get much more information. So that is a part of encoder where we transform this input embeddings such that they're actually pretty better, right? Sorry for that. So yeah, we have looked at how we can transform this input embeddings, right? So how we can add other important information that can help the output layers to actually detect better, right? So we have to actually understand how we can get, like, for each word we are going to calculate the attention, right? So how much our attention and how much importance that word has to or how much related is that word to other words. You have looked at that, how we can do that. We have QKV, like vectors, query key and values, right? So that is the ideas. Now let's look at the decoder part. So in this decoder part, there are not many more new boxes. There are not any new boxes, as you can see. There is masked multi-headed attention, which is just adding a mask. I'll tell you about that. In the last video also I have elaborated a little bit, but in this video I'll tell you about that. And then we also have this new type, right? So this is called cross multi-headed attention, even though the name is not specified there. So the idea is we can just find the attention of the word in this output with the words in this input. So I'll tell you about that also. And then we also like normal residual connections. We have some normalizations, feed forward and linear and softmax to predict the output probabilities. So first we'll talk about masked multi-head attention. What is masked multi-head attention? So right, so what is masked multi-head attention? So the idea is nothing, the idea is simple. So for example, if you're training a model, let's say if you're training attention muscle, or if you're training a transformer, let's say the actual sentence is I am Joel. Sorry, not I am a Joel. That's actually yeah, I am Joel, not I am a Joel. So I am Joel, right? So I'm this is just like, for example, let's say this is the sentence that the model should generate. Like in the target, we have this training data, right? Then the training data, we have this actual answer. So let's say this is the actual output that the model is required to generate. Let's say, so let's say the model want to predict am. Let's say model want to predict am. So we only want to input the model with I only, right? So we only want the model to know I, right? So the model should predict am from I. It's just common sense. We don't want the model to be to get the answer, right? So we don't want to reveal the model. We don't want the model to cheat. So therefore, we only give the model the previous output. So when the model is predicting this word, second word, we are only giving the model the first word. So the first correct answer, and then the model is required to predict the next word. So that is the idea. So we'll just mask off these variables. So how we do this? So let's say this is our matrix. So what we'll be doing is we'll just add this vector. We're going to show what that. So let's say we have three elements to each row. So we're going to have this thing. It's something like that. So what are we doing is we'll just adding these values. So whatever values are there in this corner, right? Of course, where will be get will be like it's like identical. We'll get all those values and we'll remove all these values by adding, let's say, minus infinity, right? Yeah, I think, yeah, minus infinity. or I think plus infinity, right? And then when we run the softmax function, all these minus infinities will be, or all these plus infinities will be turned into zeros. So therefore, we'll be able to mask off this value such that the model can cheat. That is the mask multi-head attention. And then we'll add a normalization. Nothing new about that. We'll have a residual connections just to make sure that the signal is strong and learning is happening. We don't want the model to be stagnant and not learn, right? So we to make sure that we do not encounter the problem of vanishing gradient descent, right? Vanishing gradients. We add residual connections, and then next we have multi-head attention, but the the key and value vector are from the output of encoder. So the encoder's output will be the key and values of this multi head attention block. Right. So what we are going to do is, let's say, I'm just going to give you an example just to make sure everything is going to be clear. So let's say the input sentence is who are you, right? Sorry. So let's say the input sentence is who are you, right? So who are you? The question. So we are going to get that as the input embedding, right? So at this input embedding, this is going to be the input of the encoder. And then let's say the output is, let's say the model already generated I. So let's say right. So I'm just going to go the picture for you just to make sure it is clear. So let's say the model takes in the value. It doesn't take anything at the output embedding because it hasn't yet generated the output. So first, let's say we give the start token will be given. So the model is required to start, and then we'll run through all that. No process will be there. We will, let's say we generate the word I. Right. So after generating the word I, let's say what we are going to do is, right. So after generating the word I, we will input the word I to this input embedding. So the output embedding will now be I, as the model already generated the letter I. So I will be inputted, we'll perform all this thing. And then after we have performed this mask multi-head attention, after we have performed mask multi-head attention, there is nothing much because there is only one word, right? So we need two words to actually perform mask multi-head attention. But there is a start token, and then after we have perform marks and multi-head attention, what we'll do is, right, we will compare this I, right, with every word in the input embedding, right? So we have this input we have this input sentence, right? So each word will have QKV vectors, query value vectors. So what we'll be doing is we'll be comparing. So we'll be taking these values, right? And so we'll be taking these values and multiplying that by a new set of weights, WKX, let's say. WKX. WKX. So we will be multiplying WKX by who, or the input embedding of who. And then after we have multiplied these values, we are going to multiply that by the query vector that will be also be WQX times I, the input embedding of I. We are going to multiply this by this, so just to make sure that how similar both of this who and I are. So what we'll be doing is we'll be doing WQX times I, the input embedding of I, remember, right? So what is the embedding of I, and then word embedding of I, and then we'll be multiplying that by WKX of who, word embedding of who, and then we'll perform softmax and all that. You have learned that in the last video. What we'll do to actually perform mask multi-attention. So we'll be performing attention for each of this word with I, right? So we'll perform. So we'll take the input embedding. So the output that is generated in the model will be compared to all of these inputs just to make sure to generate the next word. So that is the idea of cross multi-head attention. We'll be actually comparing the inputs and outputs, how related is the current word in the question, so in the answer with the question. And after we have generated, so that is how we can generate it. That is how we can generate new words. So in the training process, this is how the training process will happen. I'll just go through what are the steps that are carried out in the training process. So first we'll have this input. So let's say we have this input, who are you, or something like that. After we have performed the multi-head attention, we have this feed forward network, which will of course predict the output, right, of this encoder. And then what we'll be doing is, as there is no word, right, so if the model is just started, if the model just finished the part of the encoder, right, we would input the model with the start token. Start token is nothing but it specifies that a sentence can be started. So start token will be given to the model, right, and then the model will do all of this process, and then it will generate an output. It's based on let's say, right, so there is also the question, the right, so there is the model will also consider the question, and based on the question it will generate the first word. So it will be trained, right? So overall, like, it will train on questions and answers based on its experience, and based on the question it is going to generate the first word. And then after it generated the first word, right, we will take that first word. Let's say the first word is I. We'll take this I and input to this decoder again, and then after performing this operation, it will compare all of this this the current word with this all the words in the question, right? It will calculate the attention, and then we'll have another feed forward neural network. We'll do linear softmax. So we'll have a softmax to actually predict the probability, and then we'll again get this output to this input. So we'll just, whatever is the output of this decoder will be input to it again in the training process, or even in the normal process, right? So whenever a decoder is generating an output, this output is going to again get back here. So essentially what we're doing is getting the previous word and predicting the next word. So that is the idea of not only previous word. I'm just going to that confused me a lot actually. So we are not only going to take the previous word, but all the previously generated words, or whatever all of this previous generated word embeddings. We are going to take them and again input those matrices to our decoder so that we can predict the next word. So that is the idea of decoder, right? So hope you understand that. It's actually like pretty simple, I believe. Like we have this repeated parts: multi-head attention, masked multi-head attention, cross multi-head attention. So, and then we have this residual collections, and then finally we have this softmax layer to actually predict the output probabilities for what is the next word that it has to generate. So we have this corpus, right? So all of this training, so all of these words that the model know will be actually, in like it is called corpus, and based on this corpus, it is actually going to predict the probability for that next word. So that is the idea. That is the idea of this model, right? Now let's look at a implementation implementation, right? It's actually in PyTorch, right? It is implemented in PyTorch, which is actually, if you are aware with TensorFlow, you can actually understand PyTorch very easily, right? So if you like we are again going to do scale for dot product action. You know about this. You know about positional wise feed forward, like normal feed forward neural network, and then we layer normalization also, subtracting mean and dividing by standard deviation, right? And then this is the thing. So we have multi-head attention, right? Yeah, so we have multi-head attention, which is again the normal attention, but we are going to add some masks, I think. Yeah, so yeah, this is normal multi-head attention. Actually mask multi-head attention, right? We are going to calculate scale dot product, and then yeah, sorry for that late. Yeah. So first we are going to calculate scale dot product from QKV, and then also mask. We have also this mask value such that we can actually, as if you can look at this function, right? So we also have another parameter mask, right? So mask equals none is nothing but if no input is given, mask will be none. If we want to do mask multi-head addition, we can actually input the mask. So what we'll be doing is we'll be adding mask, right? So we'll be adding mask vector to this output, right? After performing scale dot product, of course. So that is mask multi-head attention, and then this is multi-head cross attention. As you can look here, we are going to have a KV layer, which is actually another dense layer, So we are going to have dense layer on top of this previous outputs, or sorry, the question outputs. So for every word in the question or the input, will be performing this KB layer, and then we also have a Q layer for the current word, right? So as you can see here, just the same thing. We'll be reshaping. We'll be doing scale dot product attention. We'll reshape, and we'll have a linear layer as the output, right? And then this is the final decoder layer. Using all of these previous classes, we'll be constructing the final decoder layer. For that, so we have many. We'll be initializing many functions or many classes. So we'll be initializing. All right. So we are going to have this final decoder layer in which we initialize all of this previous not only all of these previous classes that we have implemented, but also dropout, and we have this multi-cross attention, dropout, and yeah, we essentially we have initialized all of these previous classes that we have defined, and then we'll be performing all of this, right? So we'll be having forward function, which is nothing but performing the scaled. We are just going to implement this figure again. We're going to have multi attention, normalization, cross multi attention, and all that. Right. So we're actually going to implement that again. So cross multi attention is also called as encoder decoder attention, right? And then we're going to have dropout, normalization, and all that. So yeah, I hope you can understand what is going on, the implementation. In the next video, we are going to implement it in TensorFlow. I will try to implement it because I think these two videos, the past two videos, I have given more priority to theory, and in the next video we will be implementing this. So stay with me, and we'll be doing it. So thank you for watching, and I'll see you in the next video.